I'm Daniel Verscharen. He's a senior research fellow and lecturer at the Millard Space Science Laboratory at UCL, and he's also an affiliate assistant professor at the University of New Hampshire. Today, Daniel is going to be speaking about kinetic physics, collisions, and turbulence in the solar wind. So before we get started, I just wanted to flag to everyone that we're going to be recording the seminar, and we'll stop recording at the end of the seminar and before the question time. So anything which you do say during this period will be recorded, and we will make this public to the rest of the community after the meeting. And just to remind everyone to please make sure that you have your mute on, so we don't have any disturbances. And finally, I just wanted to say thank you to Mariana for helping us host this meeting and using the Zoom license from Aberystwyth University and Queen's University. Okay, so I will hand over to you now, Daniel. So yeah, over to you. Thank you.
Okay. Yeah, thank you very much, Jasmine, and the other organizers, and also thank you to everyone for being here, for having another online meeting. So I hope it won't be too tiring. If you have any questions, maybe the chat can work. I don't know if I will have the chance to look at that in between, but if more and more things come up, maybe one of the hosts can just interrupt me, and then we can go to the chat and look at that, or otherwise we'll just do it afterwards. Yeah, so I would like to speak about multiple things today. So it's the subtitle says a multi-scale perspective on some processes in the solar wind. That's actually my own research field, is the kinetic physics and turbulence in the solar wind. And most of the material I'm going to show today is from a review article that was published last year in Living Reviews in Solar Physics. So when I spoke with the organizers, they said it would be nice to get a more like an overview topic, because there is a broader audience here in this MIST community. So of course, don't expect that you're all kinetic physics experts in the solar wind or something like that. And so, yeah, I wanted to keep it on this level of the review article. At the end, you will also see the reference for this article. And of course, at the beginning, I would also like to acknowledge the co-authors that worked with me on this article: Ben Maruca from the University of Delaware, and Chris Klein, who's now at the University of Arizona. Okay, then, yeah, let's start right away. If any solution comes up with a full screen sharing, just also interrupt me, okay? If not, we will just do it with the slides as they are now. Okay, so, yeah, the solar wind. This is just a brief introduction slide to give you a feel for the plasma parameters, the typical plasma parameters in the solar wind at 1 astronomical unit distance from the sun. I guess you're all familiar with plasma in general, so I don't need a general introduction there, but the plasma conditions are of course a bit variable. I will focus mostly on the fast solar wind. So we have flow velocities or speeds here of about 700 kilometers per second. Like with all the other parameters on this slide, all of this can vary a lot with time, depending on where you are in the heliosphere. This is just a number for the fast wind, 700 kilometers per second. Magnetic field strength, about 10 to the minus 5 Gauss, also varies a lot. And when we talk about turbulence, you will also see that just the turbulence itself puts variations on these numbers that are quite large. Proton temperature, about 100,000 degrees Kelvin in the fast wind. Plasma beta, so if you put these numbers together with a density, and you have a density of about 3 protons or something like that per cubic centimeter, you come up with a beta that is roughly of order 1, which is a bit of a problem, because you can't work in the low beta limit or in the high beta limit if your ordering parameters of order 1. And also for that, a lot of variation, right? It can be a few percent, or sometimes it can be even 50, 60, 70 or something like that at 1 AU. And probably the most important parameter on this slide for the topic of kinetic physics, the collisional mean free path, very large. It's about 1 astronomical unit. And so it is roughly the size of your system. And so we have to consider that the solar wind is a collisionless plasma, and collisionless physics is important, non-equilibrium processes. And you will see in a moment what that means. As I said, in terms of the variation, so these are some plots. You're probably more familiar with them from the original publication from Dave McComas in the 1990s from the Ulysses observations. But we had to reproduce some of the figures for the review article. So whenever you see this reference here on the bottom, this is the review article. And these plots now, they are polar plots. And the distance from the origin basically shows you the speed of the wind at that heliographic angle, so at the heliographic latitude. This is the angle. So here you would have the equator, the sun. Here you are above the poles of the sun, right? And then you go the southern hemisphere, the northern hemisphere. And you see here the fast wind, right, with these velocities that I mentioned earlier, 700 kilometers per second, very steady above the polar coronal holes. And then when you go into the equator, then you have a bit more variation in the solar wind speeds, and it's generally slower, at least on this panel on the left. The panel on the left shows measurements during solar minimum time, and then we have this nice fast wind over the poles, slow winds near the equator, right? And here on this side, you already see, well, there's already more variation going on. This is mostly a time issue of the time of the orbit at that point. And here on the right-hand side, you see the picture now during solar maximum. So we don't have this nice structure anymore where you have fast wind over the poles, slow wind near the equator, but you have fast wind, slow wind, always like going up and down at all different heliographic latitudes. And that's just, because the magnetic field in the corona where the solar wind starts is a lot more variable during this time. And it's not so nicely polar structured like on the left. And so you get all these different sources mixed up at all kinds of latitudes. Okay, so just about that was just the introduction about solar wind so far. And now I said we have the multi-scale perspective. So the question is, what do I really mean with multi-scales? And that's from wherever you're working on in terms of space plasma, for example, you will always deal with different spatial and temporal scales, right? So whatever the problem is you're looking at, it is associated with different scales. And here I list in this diagram, list some of the characteristic length scales in the solar wind. And so we can start here with the largest scale. So L is roughly the size of the system, which goes from 1 astronomical unit to maybe the size of large coronal structures near the sun, right? So on this side, we always have the smallest version here in this magenta side, and the cyan side is basically the big 1AU picture. The next large scale here, the collisional mean free path, and you see, well, it goes, as I said before, from roughly the astronomical unit, the size of the system, but it can already be significantly smaller when you go into the corona, right? Because the density is higher, so you have more collisions there. And then here we have the other characteristic plasma scales, so the proton inertial length, for example, the proton gyro radius, again valued at 1AU here on the right-hand side, coronal value on the left-hand side. And then the electron scales, even smaller than the proton scales. So here the electron inertial length, the electron gyro radius, and the smallest scales that we're dealing with, the Debye length. And you can calculate them for both species. Don't necessarily have the same meaning, but you just plug in the parameters and you get to the smallest scales here, which is just a few centimeters, right? And you already see the big problem in this multi-scale perspective is you cover a very, very wide range of scales, right? So we go from a few centimeters to something that is AUs big, so it's 12 orders of magnitude. Of course, a big challenge if you want to simulate anything with a computer simulation. If you really want to cover all the physics, then you would have to cover these 12 orders of magnitude in length scales. You can also look at this in terms of time scales, so that is shown in this picture. Don't want to go through the details, but it's basically same connection here where you have the expansion time, collisional time, and then times associated with gyration, plasma oscillations, and so on. And likewise, you see here that this goes over many orders of magnitude, right? So here we even have like 12 or more orders of magnitude. Now, what I want to do at this point is have a little exercise with you. So I have to share a different screen now. And the different screen is this one. So now please take your computer or your mobile phone or whatever you have and go to this website that you see at the top, menti.com. And there you will be asked to put in a number. The number for this is just this one here, 119855. And then your phone or your computer will ask you this question: what plasma scales are you most interested in? And what I just want to do at this point is you can type in one answer, you can type in two answers, and then they will start to pop up here on my screen. So we'll just collect this for a moment. And as you go along, we just get a picture, a word cloud basically, of what the MIST community is working on in terms of plasma scales. So we already have the first entry, system scale, great, inertial scale. So, and you see, as you go on and put in information, you will see how this word cloud is growing. Okay, the fluid scales, great, yeah. So this is, of course, mostly stuff that happens at scales where you're above the inertial length and the gyro scale. Of course, there are also fluid pictures that would work at smaller scales, large scale solar wind, so really about the expansion, great. So this is already growing, so more people interested in that. Very nice. The fluid scales are growing. Okay, we'll just give it another moment to see what's going on here. Ion gyro scale, okay. Good, comes up a few times in different ways of writing it. Okay, we already have 23, 24 answers. Excellent. Now we'll take a screenshot of that afterwards and put this into the slides. Then we have a nice picture of the scales that the MIST community is working on. Cool, kinetic scales, Sun, Earth, yeah. Finite Lama radius effects. Also people working on multiscale effects, very good, magnetospheric scales. Yeah. Okay, maybe just give it another 15 seconds or so, and then I'll stop it. Switchbacks, yeah. Earth radii, yeah, I would imagine that for the magnetospheric community, that's really the typical scale they are working with. Okay, so we're going 5, 4, 3, 2, 1. Close voting. Okay, great. So yeah, so here we have a nice overview now over these different scales that we are working on. As I said, I will keep this, but now let's just flip back to the presentation. All right. Yes, so let's start with the first point mentioned in the title, kinetic processes. And when we talk about kinetic processes, the most important quantity there is basically the particle distribution function. And so here's try to keep the mathematics load in this presentation low, but this is probably the most mathematical slide in this whole talk. So just bear with me here. So F, distribution function, basically just represents the number of particles that are within a certain volume of phase space, so that have a position between x and x plus a small dx, and that have a velocity v plus and between v and v plus a small dv at a given time t. And so you see these are all vectors, right? So we have a total of 3 components here, 3 components here, plus time, so 7 dimensions to deal with. Again, numerically, that's very challenging, but the things that we are probably more familiar with are the moments of this distribution function. So you can integrate it over all of velocity space, you get rid of 3 of the coordinates here. And before you integrate, you multiply with different factors of v. So v to the 0, to the 1, to the, and so on and so on. And these give you the so-called bulk parameters, or the moments of the distribution function. If n is 0, then you end up with the particle density. If n is 1, then you get the bulk velocity. Of course, at that point, you don't know it yet, so you would leave this out. And then if you go to higher orders, you get the pressure tensor, you get the heat flux, and so on. And you can basically go up to infinity in your order of n. And the most central equation to describe the distribution function is basically the Boltzmann equation, written like this. So yeah, again, as I said, I don't want to go through the details. Here you would have the effect of the electric and magnetic fields on the particles, and on the right-hand side, you have the collision term. As I said, collisions very infrequent in the solar wind, at least for the protons. So usually we set this equal to 0, but we'll look at that later. We'll see what's a bit more complicated than that. Okay, so but all this information about density, bulk, speed, the temperatures, and everything that the particles are doing is basically included in this distribution function. So let's look at that in a bit more detail. And the easiest or the simplest case to look at is just the 1D case. So we have only velocity going in one direction, and we say we have enough collisions and the plasma is in an equilibrium. Then it would just follow the nice Maxwell distribution. So yeah, it's almost really the simplest case you can imagine. So then the distribution function just looks like this. As a function of v, it's just a Gauss curve. Here it's shown on the left-hand side, and it only depends on the density of the particles that defines the the height of this bell curve, and on the temperature that defines the width of this curve, and the mass of the particles, right? So this would be a 1D representation of a Maxwellian distribution, collisional equilibrium. Now we go one dimension up. So we look at this in 2 dimensions. Of course, illustrating that in 2 dimensions is a bit more difficult. So what I did here is just plotted the x component of the velocity and the y component of the velocity on these 2 axes, and then plotted isocontours of the Maxwellian distribution. So what this is you're basically looking at a bell curve from the top in 2 dimensions down, right? So we're sitting above the center of this bell curve, and we're looking down, and we see the contours like on a map of a mountain. So here's the highest value, and then it drops off like this exponential term, right? So this would be nice circles, everything symmetric, a 2D representation of a Maxwellian distribution. Now in 3D, it's even a bit more complex than that, right? In 3D, it would then be a sphere would be one way to represent that, right? So now we have the 3 velocity dimensions here, here, and here. And then you can plot an isosurface, right? So a surface where the distribution function has a constant value. And of course, in this case, if it really just depends on the distance from the center, just on V absolute here, right, V square, then the 3D distribution would just be a sphere if you represent it like that, right? So 1D, a bell curve, 2D, circles, 3D, a sphere, in this way of representing the distribution. Now let's look at the solar wind and what we really see. 1D case. So these are measurements now from wind. And you already see, so this is the speed here, and here you see the value of the distribution function on this axis. These curves here, they are the nice bell curves, right? If you show them in a Maxwellian, in a logarithmic plot, then of course a bell curve would just be a parabola. But these are basically the 1D Maxwellian curves. And these little points here, they are the measurements. And you already see the measurements don't follow the nice Maxwellian parabola, right? So what that means is collisions are not efficient enough to keep the plasma at the Maxwellian shape of the distribution, right? You also see, well, these distributions, they look different for the different species, right? Helium, oxygen, neon are shown here. And they have slightly different deviations from this Maxwellian. We also find that, for example, these different species have sometimes different temperatures, right? So for example, the helium particles are often hotter than the proton particles. The electrons in the fast wind are often colder than the protons. In the hot wind, in the slow wind, they are often hotter than the protons. We also see some of these species are drifting faster than the other species. So it's getting really complicated, and we're not in this nice Maxwellian equilibrium anymore. We can also look at 2D distributions now. Remember, the Maxwellian case was just circles, but we really don't see circles in the solar wind. So here are these famous measurements taken with Helios of 2D velocity distributions, right? As I said, if they were Maxwellian, they would be circles, but they are not, right? We see they are elongated in this direction. This is what we call a temperature anisotropy, right? So this line here shows the direction of the magnetic field. And you see the distribution is wider in this direction than in that direction. So that means we have a higher temperature perpendicular to the magnetic field than parallel to the magnetic field. Call this a temperature anisotropy. We also see there's another little bump here where the distribution goes up again. So there are more protons flowing in the direction along the magnetic field. They stream through the rest of the protons. And this is what we call a beam, right? So there's a beam in the proton population going faster than the rest of the proton. And we can even look into the 3D case. So remember in the Maxwellian case, it's just a sphere. So this is now also from a Helios measurement. You already see it's not a sphere. It's a funny shaped potato, right? It's not a sphere. And also here you see we have a temperature anisotropy, right? So this dimension is wider than that dimension. Or I have another example where you can also see the beam, right? So this is another potato example where you see that there's a beam along the magnetic field here, an enhancement of the protons in this direction. And what that means is if we don't have Maxwellians, we should be quite careful using fluid descriptions. They can still say things about the plasma behavior, but on the other hand, if the distributions have a weird shape, then in your moments, if you want to describe the plasma, you have to go quite high in the order of the moments to have a complete description. And all fluid models basically stop this moment hierarchy at some point, and then you always lose some part of the physics. The question is just how important it is, and that's of course an important question to discuss. Okay, here's another example. So we also see this for electrons. These are Helios measurements of electrons. Unfortunately, Helios could only measure them in 2D. With Orbiter, it's very exciting. We're now measuring electrons in 3D. Parker Solar Probe can also measure electrons in 3D, and we have other examples in the magnetospheric context. But solar wind 3D electron measurements were actually quite difficult to get. We have some from cluster, which are also really good. Here you see also, like, these are not circles in the 2D example. This is enhancement here along the direction of the magnetic field. We call this the Strahl. It's just the German word for beam. It's for historical reasons, they use the German word for that. So yeah, a population of electrons that run through the rest of the electrons faster than the so-called core here in the middle. So yeah, just the key message here is, so the distribution functions that describe all the particles in the system are a lot more complicated than what you would expect from a collisional Maxwellian equilibrium. And this can create a lot of interesting physics. We'll go through a few examples in a moment. Yeah, just another summary slide. So you see again, right, the protons on the left. For ions here, this is the proton core. And you have the proton beam, this other species here. The alpha particles in this example, they are also a bit offset with respect to zero, right? So they flow through the rest faster than the proton core. And on the electron side, I already mentioned that, so I don't want to go into too many details here about this. Okay, now the question is, how do these deviations form? So I already said, if we have not enough collisions in the system, then these deviations can exist, right? But it's not the same as to say, like, okay, well, but where do they come from, right? And there are multiple answers to this question, and none of this is really confirmed yet, and we don't really understand where these kinetic features come from. But one very important aspect is this change of the multiple scales, right, that I mentioned at the beginning, and how these scales in the plasma change with time as the solar wind expands from the sun to 1 AU. So in this plot, you see some of the key parameters of the solar wind as a function of distance from the sun. So here we start at the sun, we go out to 1 AU. On the top, you see the same scale in terms of solar radii, if you're more familiar with that. So we start at 1 solar radius, and we go to 215, which is just 1 astronomical unit. And you see the flow velocity of the protons stays roughly constant. The density, of course, as you go away from the sun, drops down very quickly, right? When the speed is constant, it drops like 1 over r square. Likewise, the magnetic field drops off quickly, right? So you see the magnetic field here on the axis on the left goes down by over 5 orders of magnitude as you leave the sun. And then also, I mean, just on the bottom to illustrate, you also see how that changes your characteristic scales again, right? So here we have the inertial length, the gyro radii, and the Debye lengths again for the system, and you see how they change with distance from the sun, and likewise the collisional mean free path. But let's focus on these changes for now, because there is just what you're probably most familiar with. For example, if you think about the conservation of the first adiabatic invariant, right? It's related to this CGL invariant here on the right-hand side. So if you have a change in B that is slow compared to the gyration of your particles, then the perpendicular speed of your particles changes, and that corresponds to a change in the perpendicular temperature of the particles, right? And so as the plasma expands and you lower the magnetic field, T perpendicular has to go down if it just follows this CGL invariant, right? And there's the second CGL invariant here that connects magnetic fields and density variations with the change in parallel temperature. So as soon as these two start to drop with a different dependence, then you also get a change in the parallel temperature of the plasma. So even just from this very simple expansion picture, you would expect that these temperature deviations are set up. It's a bit more complicated than that, because the right-hand side of these equations are actually not really zero. In the real solar wind, because you have heat flux, you have local heating, and also the effect of small collisions near the sun that change these equations. But to a very first order, we actually see some radial trends that are consistent with this picture and with this adiabatic cooling. But it's just also to say that the cooling itself is not really adiabatic as exactly described by these equations. So just to make this point, as soon as you have an expansion, you would expect changes in the plasma parameters coming with that. Okay, now what do these deviations from equilibrium actually do to your plasma? And that's shown on this slide as one example. So as soon as you have these deviations from equilibrium and you have a temperature anisotropy, for example, you can drive plasma instabilities. So in this plot, sometimes called the Brazil plot because of the shape of this area, on this axis we have the beta of the protons in this case. So these are proton measurements in the solar wind. Beta of the protons, and here on this side you have the temperature anisotropy, or just the ratio between the perpendicular temperature and the parallel temperature. Right? If this is 1, then you would say, well, the plasma is closer to the equilibrium because both temperatures are equal. And if you're somewhere else away from 1, then the plasma is anisotropic. And these lines here, they give you thresholds for different instabilities that can be driven if the plasma is unstable. So here in the middle, we are in the completely stable regime, but if T perp over T parallel is greater than whatever this line tells you as a function of beta, then you would expect the driving of, in this case, ion cyclotron waves from this instability. Or likewise, if you're at this point, then you would expect the driving of mirror mode fluctuations because of the temperature anisotropy instability. And you also have examples on the bottom for the 2 fire hose instabilities. And you already see, right, the solar wind populates mostly, and remember this color scale here is logarithmic, so it shows it's basically a histogram, how many measurements you get at these different locations in this plane. And you see mostly the solar wind is really confined to the stable space. So these instability lines, they put limits on the distribution of the plasma in this space, right? So you can't have a crazy plasma here that is high beta and has a very high temperature anisotropy. There's still a lot of open questions about this, about the details where these lines really lie and why there are some regions outside of it and why a lot of this is here and not actually near these thresholds and so on, but I don't want to go into those details either. Just want to say these instabilities apparently have, or they apparently do really something to the solar wind, and they limit it to the stable area. And also remember, when you if you create a temperature anisotropy, for example, by expansion, and you get to this point, and the expansion has created the anisotropy, so something on a very large scale, the instability will create fluctuations on very small scales. It will create fluctuations on the ion scale, so ion inertial length, ion gyro radius, for example. And so this is one of the examples where the large scale expansion actually couples to things that really happen on the small scales of the system, right? And you have this interaction between processes on large scales and small scales that I mentioned at the beginning. Another example, also these beams, right? The relative drift of the alpha particles can also drive different instabilities. So the ion cyclotron instabilities, Whistler instabilities, can even trigger oblique alpha waves and so on. And we've studied this here. For an example, from Helios measurements, where these are wind measurements, wind measurements of the alpha particle drift speed. And also here we see, well, there's also a limit put on the alpha particle drift, and that is quite important, and we'll see this in 2 slides, for the overall thermodynamics of the system. But yeah, I want to say a bit more of that. And just another example here, we also see the same effect happening at electrons. So this is now an example where we look at the electron strahl. So this little beam of electrons that flows through the core electrons, the other electrons that are around there along the magnetic field. And also that can drive an instability because it is a non-equilibrium state with the potential to drive an instability. And we calculated here thresholds for an oblique Whistler wave instability. Here you have the relative density of the strahl electrons. Here you have the speed of the strahl electrons, how fast the strahl is. This line here shows the instability threshold, and you see all the data points are on the stable side, right? If you make the strahl faster than this line, then you would trigger the instability. And so it reduces actually the strahl speed and brings it back to a stable value. And as in the case for the protons, you would expect that this creates small scale fluctuations. In this case, even smaller than in the proton case, because now we're talking about electron scale fluctuations, right? And you remember from the slide at the beginning that they are even smaller than the proton scales. And there are a lot of other instabilities that can also do this, just list them here. And by changing the electron distribution, they can be quite important for the regulation of the heat flux, and therefore also for the energetics of the plasma in total, and looking at it from a global perspective. Yeah, just this question about why this is important. This is a study that we did in 2015. We just calculated, if you imagine that you always change the background parameters, And by changing that, the thresholds of the alpha particle instabilities, they go down as you go away from the sun. Right, and so that means at every point, the instability brings the alphas to, reduces their speed, brings it to the marginally stable value, but then solar wind expands further outward, and so the instability is triggered again, and then it acts and it slows them down, and then it travels forward and it acts again and slows them down. So you have almost a continuous deceleration of these alpha particles that always keeps them on the value given by the instability. And of course, this deceleration of the alphas is associated with a loss of energy of the alpha particles. And in this study, we just quantified how much energy is lost by this process as a function of distance from the sun over the range that was measured by Helios. And this is the black line, basically. This is the so-called Q flow line here, right? So this is the amount of energy released by this deceleration of the alpha particles. And these two lines here, they are the lines that describe how much energy is needed to explain the observed temperatures of these particles. So for example, we know that the protons, they are a bit hotter at 1 astronomical unit than what they should be if they were just expanding into the free space without any interaction in between. And of course, that requires some energy, and we quantified how much energy is that, and that's the blue line. And likewise, for the alpha particles, we also calculated how much energy is needed to explain the observed temperature profiles of the alpha particles, and that's the red line. And the nice thing is actually that this continuous deceleration of the alpha particles, the black line, is first bigger than the red line, right? It's always above the red line, which means you always release more energy by this deceleration than what you would need to explain the alpha particle temperatures. For the protons at 1 AU, it's not enough energy, but as you go closer to the sun, actually these two lines come closer, right? And here at about 0.4, a bit over 0.4 astronomical units, they cross each other. So that means at that point, the continuous deceleration of the alpha particles releases enough energy to explain the observed proton temperature profiles. It's not to say that this is exactly the process that happens, right? But it just means it's a really important player in the overall thermodynamics of the system. And of course, if this trend continues as you go closer to the sun, we'll be very interested now to basically repeat and extend this with Parker Solar Probe data. How big is this effect? At some point, it will turn down Q flow, because then we get into the range where the alpha particles are accelerated and they haven't reached the instability threshold yet. So then Q flow would drop to 0. But where is that point, and how important is the alpha particle deceleration near the sun? I think that will be something interesting for Parker Solar Probe to look at. Okay, about collisions. So I said they're not very important for the electrons, so therefore not important for the protons, somewhat important for the electrons. That's true, but the picture is a bit more complicated. We have a full chapter in the review article on collisions, and also a discussion of the physics behind these collisional processes. So it's this nice illustration here that we use for the derivation. I just want to keep this in here as a little advert about the. If you want to know more about collisions, read there. So I won't discuss it in great detail. But just on the left-hand side in this figure, I want to show you that even for the ions, collisions can be important in the solar wind at times. So we defined a number, the so-called Coulomb number here, which is just the expansion time of the solar wind divided by the typical collision time of the solar wind. So what that means is if this number here is shown here on the bottom scale, if this number is large, then you have a lot of collisions. If this number is small, then you have very few collisions, right? So it's just a way of sorting the plasma roughly by the number of collisions and how many collisions it could have undergone during its travel from the sun to 1 astronomical unit. And then in this plot, we show histograms again, 2D histograms, where on this axis here, for example, we have the relative drift between the alpha particles and the protons. And on this axis here in this panel, we have the temperature ratio between the alpha particles and the protons. And you see, we go to the left-hand side of this plot where we have very few collisions. I would clearly see, okay, that's where the alpha particles are hotter than the protons. That's where the alpha particles are faster than the protons. So this is really the regime where you have all these nice kinetic processes that happen, right? But you also measure at 1 AU time intervals where the collision number is so high that all these non-equilibrium effects basically get washed out, right? So here, alphas and protons move together. There's no relative drift between them anymore, right, on this axis. And the temperature ratio between them also becomes equal to 1. That's the black line here is 1. Because you have so many collisions that, well, collisions just want to bring them back to the equilibrium where their temperatures are equal, right? So when I said collisionless, yes, that's true, and it's probably also true for the majority of the solar wind that we see, especially in the fast solar wind. But we definitely have time intervals where collisions change the physics significantly, as you can imagine. Also, then from a thermodynamic perspective. This makes a big difference, right? You would expect that this plasma behaves very different from a plasma that lives under these conditions here. Okay, but more discussion on that is in the review article, as I said. And then just towards the end, I want to speak about plasma turbulence. I know this is kind of like a difficult topic, and I hope that there won't be many people now switching off because they hear the turbulence word. So I'm not saying, don't want to stress this too much and don't want to go into a lot of the turbulence theory, but just look at that again from the multiscale perspective, because the nice thing about turbulence is that it is always a multiscale process, right? Turbulence is basically by definition something that occurs over many different scales. And so this is a composition of different measurements of the turbulent fluctuations. It's a power spectrum. So on this axis, you basically have a measure for how strong are the fluctuations at a different scale. And here you see the different scales. They are expressed in terms of frequencies, because when you measure it with a spacecraft, you only measure time variations. You can't measure spatial variations with a single spacecraft. But they are translated almost directly into a spatial variation in the plasma. And also here, right, you see we have a lot of fluctuations here. Then something changes and they don't follow this trend anymore. The trend becomes a bit steeper. This is like the inertial range. We call this the inertial range. And then there's another change here where the trend becomes even steeper at the typical scales of the plasma. So this is what I call here the FDP, FROP. These would be fluctuations that have roughly the size of the proton scales. These are fluctuations that have roughly the size of the electron scales. And you see at these points the properties of the turbulence change. But yeah, it's a multi-scale process by nature. Okay, and yeah, this happens in almost all plasmas, because as soon as you have not a lot of collisions in there, the medium would be turbulent. Looking at the time, I see I'm probably running a little bit out of time, so just skip some of these points. Just mention why do we care about this, about the turbulence, because turbulence and the fluctuations on many different scales can actually put energy into the particles, right? So it's the dissipation of the turbulence, which change these equations. On the right-hand side, this 0 here may not be 0 if you have turbulence that gives energy into the plasma. And we observe that we require heating in the solar wind, not just heating in the corona. There must be ongoing heating in the solar wind, and one of the best candidates for that is actually the dissipation of turbulence. So here we compare what would you expect if you just have expansion, for example. So this would be this profile here of a proton temperature, right? This would be the perpendicular proton temperature if you just have expansion. But the observed proton temperature follows a different trend, right? It's a shallow trend. So there must be something else happening on the right-hand side. And the dissipation of turbulence is a very important candidate for that. But again, turbulence by nature, multi-scale process that brings energy from large scales to small scales. And then in the review article, we also discuss some of the processes that can be responsible for the dissipation of the turbulent fluctuations, and we speak about resonant processes, non-resonant processes, and so on. But I will just skip this for now, because we don't really have enough time left, or I don't have enough time left for that. And that brings me to my conclusions of this presentation. So I guess one of the key points just to think about and to take away from this is really all plasmas, no matter where you deal with them, exhibit a behavior that happens on a very broad range of scales, and that includes spatial scales as well as temporal scales. And a lot of these processes actually couple across the scales, right? So for example, the global expansion that can then ultimately lead to the creation of instabilities, a very local and small scale process. And the other way around, small scale processes, for example, the dissipation of small scale turbulent fluctuations, can have an impact on the global evolution of the plasma. So it goes both ways. Some examples that are presented: instabilities, collisions, and turbulence, just to illustrate what they're doing. And here's also the reference now for the article. So if you want to know more about any of these topics, we also have a dedicated section on the measurement of these processes in situ measurements of space plasmas, and also a further discussion of the fundamentals of kinetics, then I would just refer you to this this article. Oh, here it says submitted. It's not submitted anymore. It's published in December. And yeah, and just close with these two pictures of Parker Solar Probe and Solar Orbiter, because both missions can now really measure detailed small-scale processes, and with their very special, very interesting orbits, measure them over a wide range of global scales in the solar wind, so that hopefully they will help us to bring this multi-scale perspective together to the end, so that we understand the thermodynamics of these processes of the solar wind. Thank you very much.